Okay, welcome back. All right. Okay, so it's my pleasure to introduce you to our keynote speaker, Dr. Shahrul Azman Zainal Abidin from Honeywell, Sdn Bhd. Okay, Assalamualaikum, Dr. Shahrul.
Waalaikumsalam
Good
warahmatullah.
morning.
Morning.
Okay. All right. It's our pleasure to have you here with us today. All right. So everyone, Dr. Shahrul Azman is the Director of Product Management with Honeywell Industrial Innovation Team USA. He graduated as chemical engineer from California State University, USA in 1988 under Petronas Scholarship. Okay, he received his Master in Science in Gas Engineering from University Technology Malaysia in 1996 and PhD from University Kebangsaan Malaysia in 2020 in Chemical and Process Engineering. He is a fellow of IChemE and senior member of IKE. Prior joining Honeywell, he served Petronas for 30 years with various positions and retired from company as Group Technical Authority in process modeling and optimization. Okay. Dr. Shahrul also has numerous plant operations, process troubleshooting, and process optimizations experiences. Okay. He is currently the adjunct professor for University Technology Malaysia, UTM, in also the chemical engineering field. Okay, so without further ado, okay, please welcome Dr. Shahrul Azman. Okay, so Dr. Shahrul, this session is yours.
Okay. Thank you very much for the session, Chairman, and thank you for inviting me for this session. Can you hear my voice clear?
Yes, very clear.
Okay. All right. Okay. Now let me share my screen. My topics today basically will be on the emission digital twin. This is very close to my heart. Okay. Boleh nampak? You can see my screen, eh?
Can.
Okay,
Can.
good. Okay, now emission digital is very close to my heart now. Reason being is that it's a combination between sustainability as well as process modeling. Because for the 30 years with Petronas, was doing process simulation since my day one in Petronas until the day that I retired from Petronas, and I've been using process simulation tool, many tools throughout my life. All right, digital emission digital twin is a representative of the emission, especially for the greenhouse gases GHG, and it can be categorized into two type of emission management digital twin. Namely is engineering digital twin as well as the operation digital twin. So what this emission digital twin will do is combining a process simulation model and operation historical data for engineering and operation digital twin. Meaning you cannot say to your boss or to any kind of simulation work that you don't have the data from the plan or operation, because you can actually generate those data from a first principle model. Meaning to say that when you want to come up with a digital twin data historian or data lake, you need to combine process simulation data, or some people call it synthetic data or simulated data. You need to combine those data with the operational data so that you can have a complete data lake throughout the operating envelope for the process of interest. Okay, then if you rely solely on the operational data, typically the operational data it won't cover throughout the operating envelope for that process. So that's the reason you need to combine the process simulation model data together with operational data so that you can have a complete complete operating envelope data. Then you can actually accurately determine the implication and effect of all sources of emission data will behave in the future based on your process condition change. It can be a fit condition change, fit composition, temperature, pressure of the operating condition, and it can be also equipment spec or control strategies. But equipment spec and control strategies is more related to operational digital twin. And the digital twin, you can use digital twin simulation. They can extrapolate how emission will behave in the future after all the necessary process improvement are implemented. Meaning, you can predict what will be the upcoming emission for your process by knowing what is your operating condition or operation mode that you're going to operate your plant in the coming months or coming years. As I mentioned earlier, the digital twin, you can separate them into two: engineering digital twin and operation digital twin, where the engineering digital twin is actually provide the soft sensor for the emission calculation. Instead of using the hard sensor, using the camera to detect methane or using a sniffer to actually sniff methane, now you have this soft sensor using digital twin to actually provide you with the emission values. Again, you combine the historical plant data with simulation data within the design envelope to predict the emission. No matter where is your operating condition are, you can actually predict what will be your emission because you have populated the data lake for the whole design envelope. And definitely you won't operate beyond the design envelope. That's the reason why you need to come up with the synthetic data or simulated data for the whole data lake. Then you can also have under engineering digital twin, this is online simulation emission model with input coming from the PI or data historian. Then a new process configuration what if analysis can be done by using the engineering digital twin in order for you to come up with the reduction studies. And by having this engineering digital twin, it can also do with the energy and emission optimization can be solved simultaneously. Typically, emission reduction is a resultant of the energy optimization. So with the engineering digital twin, you can actually do the energy and emission optimization. You can solve simultaneously. And when I say engineering digital twin, meaning it is not the process simulation model, but actually it's a data driven model, meaning you are using the data driven model using machine learning or AI ML to actually predict what will be the emission for the whole operating envelope. And this one is a steady state engineering digital twin, and you have this operation digital twin. This is where the dynamic simulation model comes in, where the new process configuration change sequence in term of to reduce the emission. Because engineering digital twin will tell you what will be your end state, because it's a state function, and operational digital twin is a path function, because operational digital twin is a dynamic model. It can actually tell you exactly how to get from point A to point B, while engineering digital twin, which is steady state model, it can only tell you whether you can reach point A or point B or point C. And using the operational digital twin, you can optimize operation action to minimize emission during transient as well as the upset condition. Meaning because of the operational digital twin is a dynamic in nature, so you can also do the how to minimize the emission using different paths of the or different sequence of action by the operators. Then you can also use operational digital twin in terms of improve future operation action to optimize energy and emission simultaneously. But this time, in terms of operation digital twin, it is now in dynamic mode, so that you can actually see how the process is changing with time by looking at the energy and emission simultaneously. And at the same time, also you can put the equipment degradation. You can predict the equipment degradation and time for and how to tie in the finding with the maintenance team. Okay, moving on. This is the simplified architecture how the engineering digital twin looks like. So you have your data historian, or in this case, I just use Pi system, and you have the real-time data, including as well historical data that it put in place. Then you combine this Pi historical data with Unisim. In this case, Honeywell, we are using Unisim model. You can use any other simulation tool like Symmetry or HYSYS. Then using the simulation model, you can come up with the first principle plant model. You can do energy optimization. You can do emission source sensor. You can also do what if analysis in terms of emission reduction. Then finally, you have this dashboard of engineering digital twin. You can achieve in terms of emission optimization as well as the emission reporting. Basically, in engineering digital twin is a combined transmitter measurement emission input data and actual plant simulation data source sensor to create the emission digital twin. And it can be done accurately for all 13 sources of emission sources, and also historical trending of the emission for all the 13 sources identified in OGMP emission source. And you can also use engineering digital twin to generate the inferential model to represent the hard sensors, so that the hard sensors can be relocated to other places, and you can use the hard sensor to actually to tune the soft sensor model from time to time, especially when you can detect that the soft sensor or engineering digital twins start drifting in terms of giving you the accurate result. So soft sensor is good. Reason being is that you cannot put hard sensor all over the places because it's very expensive, the hard sensors. And that's the reason that in Honeywell, we really recommend soft sensor as well, to actually to come up with the inferential model for your particular emission source, so that you can, from time to time, you only need a small number of hard sensor to actually to retune or to retune your hard to retune your soft sensor in the case where the model start to drift. Okay, this is some graphical information, and you can see that first you need to develop the Unisim model for your process. In this particular case, it's an upstream model, and and you combine with your LDAR report to segregate between leakers and so non-leakers, and then you start to model the fugitive emission coming from LDAR report. And with the sufficient emission data and inferential model, fugitive model can be developed as well. Meaning you will see, you can see from year by year how the leak is propagate with time. So from there you can have the collect the in terms of fugitive data year by year, and from there you can have machine learning also to actually predict what will be your fugitive emission for all the devices identified in the LDAR report. LDAR meaning leak detection and repair. On the left, you can see those are the for fugitive, and you can use the same model actually to model the other 12 emission sources for the soft sensor in terms of you know flaring, venting, stationary combustion, pneumatic device, acid gas removal, storage tank, and so on. You can do it in a process simulation tools. So, in short, the engineering digital twin is a hybrid data lake operation class first principle data, and you can have a wide range of operating emission data can be generated by process simulation tool for all the 13 sources of emission. Now, this is how you're going to use the engineering digital twin for any engineering optimization. In this case, I put it as a predictive data-driven engineering optimization digital twin. The first box on the left is a design limit envelope. This is where you generate the data coming from first principle as well as combining it with the historical data. And the historical data is the data that you need to reconcile first in order to be combined with the first principle data. Then when you have this data, you can locate the optimization point with current condition by solving the energy and emission equation simultaneously. And finally, you generate the emission and energy optimization envelope between the design limit. Meaning to say, for every condition that you operating your plant, you will get what will be the best energy and emission optimization point that you need to set for your controllers. So the benefit of having this kind of thing is you will be alerted when the abnormal process condition are detected or sustainability goal are at risk in terms of you have a target in terms of your emission target, and use of soft sensing to gain insight into areas of the process where transmitters are not available or feasible that impact the emission. For instance, is a heat exchanger UA, pump compressor efficiency, equipment fouling, and etc. And you can replicate process condition with the lowest and highest emission as a guide to reduce the emission. So you can trend in terms of at what condition that your emission is the lowest and highest. Is lowest emission and lowest energy or at energy optimization is the one that you want to replicate. And when it is the highest emission, this is the operating condition that you want to avoid. So it will give you some insight, actionable insight, so that you can the do and don'ts during the operation in order for you to get the energy and emission is optimized simultaneously. And you can also do scope 2 of the emission utilities in terms of simultaneous energy and emission optimization. All right, moving on. This is just the optimization digital twin in terms of graphical representation. Again, you from the bottom, we move from the bottom, historical plus real-time plant data historian. And you combine with the first principle simulated data, then you have this data-driven model within the design envelope. Then you do the predictive and optimized energy and emission model. And finally, you do the prescriptive action in terms of to reduce the emission. And we have the data-driven model on the second layer from bottom. And this is where you will send it to your dashboard, emission dashboard. In Honeywell, the dashboard called Sustainability Plus, or we call it S Plus in terms of visualization tools in order to portray or to visualize the emission condition at any given time. All right. Now we move on to the second type of digital twin in terms of emission digital twin, which is the operation emission digital twin. And this is where the OTS dynamic model come in. OTS mean operator training simulator, based on Unisim, or can be any other simulation tools. Hello, ada soalan ke? Oh, okay. Then using OTS, you can develop the actual plant model based on PNID, latest PNID. And you have a dynamic simulation model for the OTS, basically full soft sensor based emission accounting and trending. And you can also use the dynamic or OTS model to optimize operation sequence action to minimize emission during transient and upset condition. And you can also see any control loop instability during process upset that you want to tune it, and so that you can know, you can visualize during the transient how to actually minimize the instability of the process by tuning the controller tuning parameters. And you can also do a simple process and control loop modification in order for you to get the best in terms of controllability and to minimize the emission. And you can also do the what if analysis for the panel operators action to minimize the emission through the operation emission digital twin. And last but not least is the predict the equipment degradation and time for the for maintenance. Moving on, this is how the operation emission digital twin looks like. This is the process simulation tool outlook. In terms of, you can see that on the left is all the emission sources, and you can actually look at each of the emission sources. How does it changing with time for any panel operator's action? So this is in real time, and it can give you a lot of insight in terms of what to monitor, so that it will you can maintain your emission between your limit. Okay. And moving on is this is also another graphical representation of the operation emission digital twin, and you can actually play back the digital the dynamic model by reading this data coming from your historical data that you store in place, so that you can trend the how the emission, and also you can learn from the emission trend, what are the best operating condition to minimize the emission. And you can link this dynamic model. Okay, this is the how the you can link this. You can see from the top is the dynamic model. Okay, that's the top one, top left, and below it is the how the DCS look like. You can actually send this data to your data historian, to the PI that have the same graphical user interface as your DCS, so that you can do all the control, all the changes, not from that directly from the process simulation tool, but you can do it from your mimic your DCS interface. So all action or all changes by operators, it can be done through the not the actual DCS, but it's a mimic of the DCS, so that you can see the actual emission at any given time. And this is how the operation emission digital twin looks like. You will replicate your exact DCS, and all changes need to done by the operators through this interface, because not everybody is able to use process simulation tool regularly. So that's why we come up with the exact representation of the plant similar to the DCS graphics. So any action will be done through this interface. So this is the separation unit. This is the compressor train unit. All changes can be done here. And this is second train of the compression. And we also have this tank located in the terminals. Okay. And it also gives you in terms of what is the overall CO2e emission coming from the digital twin. And this is CO2e, this is methane, and we can also show the CO2 as well. And this is the trend that you can have from the digital twin. You can trend in terms of what happened if the feed buff is maintained at 50%, or you can ramp down to close from 100 to 50% within 1 hour. You can see how the emission is changing with time. And similarly here, again, you can shut down any valve so that you can see how the emission actually is behaving, so that you can reduce the emission in your facilities. Okay, that's all I have for my presentation now. I'm happy to answer any question.
Okay, thank you very much, Dr. Shahrul. Okay, so now I open for questions from the audience.
Any question, not only based on this topic, but any question about simulation also you can ask.
Okay, Dr. Shahrul, maybe while waiting for the rest, maybe I can ask one question. Okay,
Sure.
It seems like you are using Unisim, okay, for this project, okay. So what is different between this Unisim and Aspen? Because I think currently a lot of us been using Aspen Plus, Aspen Dynamics, and so on.
Okay. Okay. Good question. Aspen, they have two software, namely HiSys and Aspen Plus. Okay. And as you can see that Unisim is very similar to HiSys. In fact, Unisim, we can read HiSys model, and I'm not sure whether HiSys can read Unisim model or not. I believe they can. Okay. And Aspen Plus is different. If Aspen Plus is owned by Aspen, and as you know, the HiSys and Unisim is originally coming from Hyprotech, then down to Aspen, then Aspen have to give their source code to Honeywell, as well as they keep one copy, and another party I can't remember. It's a RefSim. I can't remember the company name. Okay, now they are all the same. If you ask me, they are all process simulation tool. They are the same. What make one process simulation tool is different from the rest, or make it better from the rest, including symmetry actually, is the thermodynamic package that they have in place. Okay, in symmetry, I know symmetry very well. Symmetry, icon symmetry, because I also developed icon during icon development stage together with VMG last time when I was with Petronas. The only difference is that what is the available thermodynamic package that you can use. One thing that I know that if you key in all the your slate, your composition slate, okay, and most of the process simulation tool, they should be able to automatically detect what are the available thermodynamic package that based on your selected composition. So they will filter out those property package that you cannot select based on your composition. So for instance, if you have all hydrocarbon, then the parameter will be there. But once you put methanol and highly water condition and CO2, then basically your high pressure condition, then automatically the software will filter for you those property package that you cannot use. In fact, you cannot select those property package. So to answer your question, they are same, but the only difference is that the thermodynamic package that they have in place for in their respective process simulation too. I hope I answered.
Okay. Yeah. Thank you. Okay, I think we have one questions in the chat box, so I will read it up to you. Okay.
Yeah,
It is
yeah.
from Dr. Sang. Okay. Hi, Dr. Shahrul. Okay. Can students get a free license of Unisim for the purpose of education?
Okay. Good question. Now, yeah, you can email me. You can get my email from the organizer. Just send email to me, and then I will respond your email accordingly, because I need to know what I need to know is coming from which university, and how many student that for that particular semester or that particular batch will be using Unisim. So just email me, then I will respond accordingly.
Okay. Okay. Is there any other questions? We still have time for this session.
Yeah, please ask question. Any question on simulation?
Assalamualaikum. Good morning. Can I ask one question, please?
Yeah, Waalaikumsalam warahmatullah.
Yeah. I just want to ask about the sustainability goal, particularly emission. How ready is actually Malaysian industry, in your opinion?
Okay, now Malaysian industry predominantly in terms of emission is mostly coming from oil and gas sector in terms of GSG. People always confuse the difference between GSG and also car. Car meaning the air quality gases versus the GSG gases. Okay, car already in place. Carbon Act regulation, something like that. Okay, now car and GSG, they are totally different. Car is concerning about air quality, meaning SOx, NOx, CO, CO2. Okay, they are concerning only on that because it will pollute. It will pollute the environment, and it's not good for the people surrounding it. No. Now GSG is different. GSG is focusing on methane, CO2, as well as N2O, and also the refrigerant that used by cars, lorry, by mobile, by all the motorists, because those are GSG gases. And GSG gases, the impact is different compared to the air quality gases, SOx, NOx, and so on. The GSG will impact the ozone layer, that will impact also the increase of temperature globally. Okay, now Malaysia already committed into curbing the global warming, and Petronas is one of the member of OGMP, Oil and Gas Methane Partnership, and they need to actually do the not only Petronas but also other company, Exxon, as well as Aramco and so on. They need to report their emission, especially methane. Because methane is more dangerous compared to CO2 in terms of if the impact to the ozone layer. And people also don't understand why global warming is an issue. I will explain a bit. Okay, so when the temperature increase globally, let's say increase 1 degree Celsius. Okay, so what will happen is that when the global temperature increase, the sea level, not the sea level, water will sea water will vaporize more. It's not only sea water, whatever water in the land will vaporize more. When it vaporize more, that means the cloud also will be thicker and bigger lah. And that's why you have very heavy rain. You are flooding throughout the world because of the global warming. Okay, so how ready is Malaysia into it? In Malaysia, we only have this air quality regulation, but in terms of GSG is not there yet. But Petronas make a very good move in terms of become a member of GMP, so that their reporting in terms of methane emission from all the Petronas facilities is monitored by this OGMP, and by become a member, the company need to show the OGMP in terms of what is their methane reduction strategy from year to year. So many countries in the world, especially US, already impose a penalty in terms of CO2e if the one particular site is emitting more than 25,000 CO2e for every single ton after the 25,000, they need to pay about 900 USD per ton of CO2e. In Singapore, they already imposed the penalty, which is only 5 Singapore dollar for every ton above 25,000 CO2e. In Malaysia, that kind of regulation is not there yet, but believe me, it will come. It will come sooner than what you thought. I hope I answered your question. All right, any more
Okay.
questions?
All right. Do we have any other questions? We still have time. So participants, if you like to ask questions, you can give a few minutes for that.
Yeah, you can ask question about simulation. I'm more than happy to answer.
Yeah, maybe I can ask Dr. Shahrul. Huh?
Yeah, sure.
Okay, Shahrul, yeah. Okay. We're talking so far about simulation, is it? I'm just wondering, kalau we have online data, how do you integrate into the simulation part now? Kalau we get online data and all that, can we integrate into the Sim or whatever? Yeah, can you just explain that?
Okay, definitely we can link your online data with Unisim through OPC communication protocol, and we're not going to communicate all the data to Unisim, but we only going to communicate the data that will be the input to the Unisim model or any simulation model. Okay, so we're going to link it with a steady state model, not dynamic model. And when your data is changing with time as an input to the simulation model, steady state model, then the simulation model will also change as required. As required, meaning it will change with time as well. Now, if your process is topside facilities or upstream model, we don't need to come up with a data-driven model, because for topside facilities, the convergence of the model is almost guaranteed. But if your process is not topside facilities, if your process is petrochemical refinery or or LNG or gas plant, then we need to do it through the data-driven model. Meaning, we develop the process simulation model that match your current condition, okay, and condition and production. Then we're going to run a case study based on your operating envelope to come up with the data lake for that particular model. Then we will use machine learning to actually to represent the process simulation model. Reason being, why for petrochemical or refinery or gas or LNG plant, we cannot do similar way of we did for upstream process. Typically for huge model like refinery or petrochemical or those kind of plants, they have a lot of recycles. And this recycle will take time to converge. That's number one. And number two, the chances for the model to diverge is very high, depending on what input is coming from. Even though the input is reconciled, but to guarantee it will converge as well as to converge in a time limit is a challenge. That's why we recommend for complex plant, you can see complex plant behind the session chairman. Those are complex plants. We recommend for the data driven model.
Okay, okay. Is it the machine learning is where is located where the machine learning part
Machine learning
inside the Unity?
Okay, machine learning, yes, is part of the it's not part, yeah, it's part of Unisim. If it's between the simulation model, but if we generate a data driven model for operating, because Unisim cannot have if the data is too big, then we need to have our another tool that can do the machine learning part, and it will communicate with Unisim.
Okay, okay, very good.
All right,
That's
thank you.
very good too. Thank you.
Okay, thank you, Prof. Azman. Okay, Dr. Shahrul, we have another question from the chat box. Okay, it is from Dr. Noraini. Thank you for the insightful sharing, Dr. Shahrul. How do you find the importance of simulation and modeling skills for chemical engineers? As in the university, we found not many chemical engineer students like to do simulation or modeling based research.
Okay, when I was the AIP, industrial
IAP.
for many universities, but APU belum lagi lah. For many universities, okay, UKM, UITM, UTP, UMP, many universities. In fact, I cannot count those now. UTM. Okay. I always encourage simulation model should be taught during the first year itself. Okay. When I was in US, I studied at US though. When I was in US, during that year using CamShare. Tak tahu whether you heard the CamShare or not. CamShare is the first process simulation tool. And we use CamShare. We use CamShare since our first semester in chemical engineering. And during first semester chemical engineering, we use CamShare to actually come up with the properties, density of composition, phase equilibrium, come up with the phase equilibrium data. So it can be taught since year one of chemical engineering, especially in thermodynamic class. So in all our chemical engineering classes, starting from mass energy balance all the way until our design project, process simulation is become part and parcel of chemical engineering, because during our exam, homework, during our homework, let's say 5 questions. One question will be simulation question. All classes, all chemical engineering classes. So the problem with the setup that I can see in all the university in Malaysia, for instance, become AIP for many universities. Process simulation tool only implemented during the final design project. And that is very, very wrong. In certain university that I become the IAP before, they also use simulation tool for their chemistry punya class to predict the properties. So then if you put those things, process simulation tool as early as possible, then you put also computer programming. Like in my case, I was studying in US last time. We introduced in second year of chemical engineering, and again, all homework problem we have one question based on computer programming, chemical engineering. So when we graduated, we are good in simulation. We also good in programming. You need to have both. both skill here to become a very good chemical engineer. Bos tu akan sayang you if you have this skill. That one I can guarantee.
Okay, so we have to have both simulation and programming skills, right, to become a good chemical engineer. Okay, we have, so I hope that answered Dr. Noraini's question. So we have another question. From Dr. Sang again. Okay, hi doctor, from your experience, how can we choose a suitable thermodynamic package like Peng Robinson or Redlit Kwong for the model developed? I often get confused with it.
What simulation tool used by APU? APU.
Dr. Sang is from Vietnam.
Oh, Vietnam. Sorry.
Maybe Dr. Yeah.
Yeah, that's fine. I assume kebanyakan orang guna Unisim or IC lah. Okay. Vietnam, I need to speak English then. Okay, now. Typically, for what people use, like myself, the way I will select, I try my best to select the equation of state first. If equation of state cannot do my job, then I go to the activity model. And why I like to choose equation of state? Equation of state, like Peng Robinson, Redlit Kwong, all those kind of equation of state, they are good for gases. Because equation of state, when they develop the equation, it based on PV equal to Z and RT. And what difference between one equation of state to another equation of state is how they derive the Z factor. Okay. I have the chance to meet Professor Peng in 2000. I remember also 17, 16. He's a professor from University of Saskatchewan in Canada. He came to Petronas. I invited him to officiate our ICON survey. Okay, during ICON conference. So when I asked the same question to him, and this is the answer coming from Professor Peng actually. Try your best to stay in equation of state if you can. But if you cannot, then you switch to activity model like Margulis. Apalagi yang lupa lah. Wilson, NRTL, those kind of. But if your simulation model is high pressure liquid phase, then use activity model. If your system is highly in gas, use equation of state. Because now Peng Robinson also have many kind of Peng Robinson. Okay, they have Peng Robinson Vera, they have Peng Robinson Wilson. Those kind of thing will actually differentiate from one equation of state to another, even though they are coming from the same Peng Robinson. But it will cater for different kind of can be high polar component, especially water. Okay.
All right. So I hope that answered Dr. Sang's questions. So I think we don't have any further questions. Maybe I can call if we have any one last questions, since we do have time.
Yeah, this is your chance to ask question.
Okay, right. So we have one more questions. Let me just read out to you. Okay, it's in the chat box. Okay, wait. No, it is actually just a quick question. Dr. Sang is following up. Maybe he heard about something on the Z factor just now, so he's asking whether that is the compressibility factor.
Yes, it is the compressibility factor. Yes.
All right. Okay, and then he just give a quick comment. Thank you for the guideline. Okay, I think we have no more further questions. Okay, so Dr. Shahrul, if I may request you to stay on the platform, okay, because we have prepared a certificate as a token of appreciation for you. So may I request the technical team to share the certificate? and help to take the picture. We'll
Okay, thank you.
Okay, this is the certificate. Thank you very much, Dr. Shahrul.